Okay, welcome to Algebra 2, Semester 2, Section 13.8, Factoring Two Terms. This is actually in Unit 8 on statistics. We're just looking at some other situations that can occur with statistics. First thing, let's warm up with the factoring. We did GCF factoring last time. So anytime you get to two terms, the first thing you should ask anytime you get to any polynomial is, can I pull anything out as a GCF? And on this first one you can see you could pull out 4. So pull a 4 out. That would leave x squared minus 4. Now when you look at two terms, there's one thing that's kind of tricky that you want to always look for. If you have two perfect squares with a minus between them, we call that a difference of two squares. So yes, there would be a difference. Are each of the terms perfect squares? In that case, that's a 1 and a 4. Yes, they are perfect squares. We're going to factor this in a new way that's really fast and easy, and I'll show you that in a minute, but I have a few of you that I'm sure are sitting there saying, what does she mean by perfect squares? We might as well get to our list of perfect squares and perfect cubes that you should memorize for this class. Right here is the bottom of the sheet. I went ahead and filled in the perfect squares and perfect cubes. So pause the video and do those, and then come back and check your answers. By 1 cubed, I am meaning 1 times 1 times 1, and that equals 1. 2 times 2 times 2 is 8, and that's 2 cubed. When we get to the squares, it's 1 times 1 times 1 is 1. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. So it really means how many of those factors there are. There's 2 3's. 3 times 3 is 9. Here there's 3 3's. 3 times 3 times 3 is 27. So go ahead and fill those in and then check your answers. Make sure that you have them right. Again, that's at the bottom of page 9. Yeah, just up above there on page 9. We'll go ahead and I'll show you, since this is a difference of two squares, it is a add-subtract pattern for multiply. So we put a minus and a plus. That's what eliminates your middle term from having 3 terms there. And now we take the root of the x, put it in the front, the root of the 4, put it in the back, and the 4. Now, like what we saw last time, factoring is the opposite of multiplying, or the reverse, I should say, of multiplying. So if you chose to distribute this 4, and then you chose to multiply this and this, then you would end up getting 4x squared minus 16. I'm not going to do that on the video, but you're welcome to do that, and come see me if you don't get that. When we get to this one, the very first thing that we see is that p could be pulled out of those two as a GCF. The other thing, 3 goes into both of those, so pull a 3 out to the front. And 3p times what would give me 9p squared? That would be 3p. 3p times what would give me 21? That would be a minus 7. I can't go any further. Those aren't a difference of two squares. There's nothing there that I can take down further. So those are your first two answers. On the next one, I can't think of anything that I can pull out of 16 and 25. They are perfect squares, but they're not a difference. So I can't do the difference of two squares pattern. So I can't see anything that I can do there to simplify it. I just circled that as my final answer. The last one, obviously 5 will go into both of these. 15 and 10 are divisible by 5. 5 goes into 15 3 times, bring down the v squared. 5 goes into 10 negative 2 times, because it's a negative 10. And that completes that. That's the end of page 9. Going over to page 10, let me just make sure that we're doing everything right. Okay, we're going to look at a couple patterns here on this one. Yeah, we're going to look at some patterns still with these, with multiplying and factoring. First one, we're going to be multiplying this. Now remember from Algebra 1 that we have to be very systematic. We need to make sure we take this first term and multiply it by everything in the other parenthesis. Then take our second term and multiply it by everything in the parenthesis. So I usually draw arrows. A times a squared would be a cubed. A times ab would be positive a squared b. A times b squared would be positive ab squared. Now when I multiply negative b times a squared, I get a negative a squared b, and I line it up underneath this one since they're like terms. Negative b times ab would be a negative ab squared, and a negative b times positive b squared would be a negative b cubed. Now when I add these terms, it's kind of unique. What I see is the a cubed gets added to nothing else, so it's fine, but these end up being opposites and they wipe each other out. And all that I have left is a cubed minus b cubed. Well, if multiplying is the reverse of factoring, then that means when I see a cubed b cubed, if I've memorized what that looked like, I can go straight to the factored form. And that's the best way to do this is memorize that formula, a minus b, a squared plus ab plus b squared. And I apologize, I know that there's some fun tunes out there to help you remember that. I don't know any of those, so feel free to hop on YouTube. In time I'll probably associate a YouTube video with this lesson so that you can hear a funny tune and remember the formula. But for right now, what I remember is just that it's just like it looks, a minus b without the cubes out front, and then everything else has positives in it. A squared plus ab plus b squared. Okay, now let's look at what happens if that negative shifts from being out front to being on the inside. Now let's multiply this. A times a squared is a cubed. A times negative ab would be a negative a squared b. A times b squared would be a positive ab squared. Positive b times a squared is a positive a squared b. Positive b times negative ab would be a negative ab squared. And b times positive b squared would be a positive b cubed. We bring down the a cubed. Our second term wipes out with the other second term. Third terms wipe out and we get a cubed plus b cubed. So once again, being the opposite of factoring, I know that I can memorize it's almost the same formula as this first one. The only difference is this will be a plus and that will be a minus. So I just remember it's a, because that's a plus, it's a plus b out front. And then it's a squared minus ab plus b squared. Whereas the other one was ab plus b squared. It was a positive ab plus b squared. So now I'll show you how I use those when I come to binomials that have perfect cubes. From the list that I just had you memorize, you know that 8 is the perfect cube of 2. So I can write that as 2a cubed minus, and I know that 27 is 3 cubed. Now I can see that that's just like a cubed minus b cubed. So I realized that 2a is going to plug into the formula for a, and 3 is going to plug in for b. So I just go ahead and use this formula, a minus b, it would be 2a minus 3. Then for the next part, 2a squared, now make sure that you get parentheses around the entire 2a squared, plus 2a times 3 plus 3 squared. I bring down the 2a minus 3. 2a squared is 2a times 2a, which would be 4a squared. 3 times 2a is 6a, and 3 squared is 9. So that's how I use that cubic formula, the difference of 2 cubes. On the sum of 2 cubes, I'll show you how I use it over here. I know 125 is 5 cubes, so that becomes 5b cubed. And 1, that unique little guy, is always his own cube, or cube root. So now I plug 5b in for my a values, and 1 in for my b values. Whoops, I'm thinking of my other formula where it's a plus there. That should be a minus. Okay, I have 5b plus 1. 5b squared is 5b times 5b, that's 25b squared. Minus 5b times 1 is minus 5b. Plus 1 times 1 is 1. So that's my factored form. Very easy to do, where I've memorized that formula for the sum of 2 cubes. There's my difference of 2 cubes when I factored it, and there's my formula. So practice those in class a little bit, they'll become incredibly easy for you. Now we're on to box and whisker plots. And I believe that that's the end of this video. No, I'm sorry, we're only starting this video. Whew, getting confused on my listing here. Box and whisker plots you've probably seen in the past. What you've got to remember is each section of the box and whisker plot is always 25% or 1/4 of the data. So you've seen these graphs, they look like this, they look like a box, and then whiskers that come out. Where I see kids get real confused is when a whisker or a part of the box might be real long, to realize that this is the same amount of data as this section here. So what I like to do is think about this like a piece of gum. And if we have a piece of gum and we draw a line where it splits in half, that would be our median. In other words, half the materials to make the gum is here and half the materials is here. Now let's go ahead and draw it like a box and whisker plot. Let's say that there's 1/4 and 1/4. Now we'll complete this 1/4 over here. So now we all agree, or I'm going to assume that you do with me, that each section has the same amount of gum. Now here's what happens, is when you have data that's spread way out, then it spreads a section out. Oh, that didn't work very well. Let's see if I can get, I broke my box and whisker. I was hoping that I could stretch it, there we go. Whoops. So you can see that sometimes, if I don't break it, a section might be stretched out, whereas another section might be all pressed together. So now that section looks shorter than this section, Well, this section still has the same amount. So I like to think of it like the Hershey's chocolate bar, where it's already got the lines drawn, and let's just say that we melt it a little bit and we can spread it out, but it would still contain the same amount of chocolate. Same thing on a box and whisker. So the first thing that you do on a box and whisker is you put the data in order. So we take this data and we'd put the lowest number first, 15. The next lowest would be 20. Then 25, 30, 40, 55, 60, and 70. All I did is I took our data and I put it in order. So to make our box and whisker, we need to split it into 4 equal parts. So the first thing that I find is the median. I start at this end and this end, I just check them off, right to the middle of the data. Just trying to find the center. My center happens to be halfway between 30 and 40, which is 35. Okay, now, in order to find the quarter up here, we have to cover all the data, including the median, down on this part. Now we only look at these values. Halfway in these 4 values would be halfway between 55 and 60, which would be 57.5. You can add those up and divide by 2, or you can just continue to go 59, 56, 58, 57, 57.5. Now to find the other quarter of your data, cover those up clear over top of the median. And now we find, well, we've got 4 values. Halfway between the middle 2 would be 22.5. So what's important in making our box and whisker plot are actually these values right here, the end values, and then these 3 values there, because that splits it into 4 parts. So we make a box. First I come down and I write the values on my number line. And in order to get all these values in here, I'll probably go by tens. 0, 10, 20, 30, 40, 50, 60, 70, and 80. Okay, now what I do is I just transfer these important points down. The 15 is the lowest point of my whisker. 22.5 is the bottom of the box. 35 would be the middle of the box. 37.5 would be upper part of the box. And 70 would be the top of my whisker. Now I add in my horizontal lines to connect all these. And then the last thing I do is label them with the amounts because they didn't line up with my number line with the number. So I show that the lower extreme is 15, that this is 22.5, that this one is 35, and that this one is, I'm sorry, I read that as 57.5. Or I mean, I read it as 37.5. It should be 57.5. And 75, or 70. Now on the 70, you didn't have to mark it where it does line up, but it's always nice to have them written up there. So, last thing here is I want you to get to know what the different meanings of some of the vocab is on Box and Whiskers. That's why I couldn't tell you what the different parts were when we were building that one. I apologize if you remember the parts. So let's go ahead and draw a box and whisker. Let's put this lowest point at 1. Let's put the bottom of the box at 3. Let's put the median, or the middle of the box, at 3.5. And let's put the top of the box up here at 5. And let's put the top whisker, or the other side of the whisker, up to 6. Now, the interquartile range, you'll see this labeled as IQR. It is equal to your upper quartile minus your lower quartile. Well, at this point, if you've forgotten the meanings or the names on the different parts of the box, you're probably sitting there saying, well, that doesn't help me at all. We do know that the middle of our data from previous lesson is the median. So we could label this as median. Now going out from there, this is a quarter of the data, right? 25%, or a quarter. So we call this an upper quartile. And down here, this is a quarter below, because remember, no matter what size the box looks like, it's a quarter of the data. So this is the lower quartile. And now, out at the ends of the whisker, we call that a lower extreme, kind of like the skateboarders that do things way out on the edge. It's an extreme. That's what I think of in these graphs. So this would be an upper extreme. So now you can see at the bottom of page 10, when I ask for the interquartile range, I'm asking you to give me the formula upper quartile minus lower quartile, or it's the length of our box. So it would be 5 minus 3 in this case, which is 2. Interquartile range is just the range within the box. Now, looking still at that graph, I want you to give me the lower extreme, the lower quartile, the median, the upper quartile, and the upper extreme. Pause the video, make sure that you understand how I just got all those. If not, then feel free to look back over what I just explained, or look at other YouTube videos on Box and Whisker. Okay, now we're going to have interpretation of Box and Whiskers. These occur a lot of times on standardized tests, so let's make sure that you understand what these are. It's precipitation in inches each month in Dallas, Texas, and in Houston, Texas. This Box and Whisker represents the rainfall in Dallas for each month. This represents the rainfall in Houston for the month. So for example, like, let's say that their driest month is July. They get 1.9 inches of rain in July. That's where that 1.9 came from, is the data from July. So, for how many months is Houston's precipitation less than 3.5 inches? So what you want to look at is 3.5 for Houston, and it happens to line up right here. It says how many months is less than. So we're talking about down here, well, we know that that's 1/4 of the data. And there's 12 months in a year, so 1/4 of 12. Write the 12 over 1, we get 12 over 4, which equals 3. So for 3 months, they have less than 3.5 inches. That's how you'd get that off the data table. The next one, compare the precipitation in Dallas with the precipitation in Houston. Well, if we look at this, we can see Houston gets a lot more precipitation. Okay, the lower level, or the very bottom, the lowest extreme on Houston is still above 75% of the rainfall in Dallas, because there's 25, 50, 75%. So that could be a valid thing to write here, that rainfall in Houston is greater than 75% of the months of rainfall in Dallas. Okay, I didn't realize until I was reading these graphs how much wetter Houston is than Dallas. Okay, and you may have some other comparisons that you want to say. You may even turn around and say, well, 3/4 of the year Dallas is drier than Houston. Okay, now during this one wet time for Dallas, it is very wet. You know, it has a heavy amount of rainfall in that one period of about 3 months. So you may even say that Dallas has some real torrential type rains during just a short segment of the year. For how many months was the precipitation in Dallas more than 2.6? Well, we see 2.6 is the median. Median is halfway in your data, so that means 6 months out of the year, the precipitation is 2.6 or greater. An outlier. An outlier is a data point 1.5 times the IQR, which is your interquartile range, greater than I should have put the outlier is a data point that's greater than 1.5 times your IQR. So in other words, if you take the length of this box, measuring it, it's about 3/4 of an inch. So 1.5 times that would be 3/4 plus 3/8. So it would be about that far away. If you had a data point up in here, you'd show it as a point. Okay, and that would be an outlier. It's away from all the other data. And actually it would be that far from that point, come to think of it. It would be like way up there. Okay? That would be an outlier. And usually you don't have too many outliers, but they're obviously visible. As I just showed you, it's graphed at the end of the box and whisker with a point out there. Okay, that brings us to an end of the notes on box and whisker and the factoring. Thank you very much.